With silicon pushed to the limits, the future of computer chips is smaller, faster, and cheaper. With a growing demand for smaller electronics and better LED devices, a research team at St. Louis University is responding by developing a new way to grow nanowires and other nanostructures for emerging technologies. It's one of the trendiest areas in modern science, building very small things in measurements of nanometers. From nanowire sensors for medicine to exceptionally small electronic circuits for everyday devices, something so tiny has enormous impact.
It could be used for photodetectors, it could be used for chemical sensors, for biosensors. Everywhere we look today, there is some kind of device.
Taking something as tiny as single atoms, this lab is making big strides.
We grow a variety of materials: nanowires, carbon nanowires, metal oxide, zinc oxide nanowires. We also grow semiconducting two-dimensional crystals.
St. Louis University researcher Dr. Irma Kuljanishvili has developed a promising technique to produce nanoscale materials using simple processes. With this lab's approach, the team is successful growing nanowires out of zinc oxide with diameters about 1,000 times smaller than the width of a human hair. Nanowires are like electrical wires.
Nanowires they're very interesting. They're one-dimensional, so they're very long usually, and they have very small diameter. It was unique in its way that we were able to control the nanowires that we grew.
The lab innovates, finding new ways to grow nanowires and two-dimensional nanomaterials. They start by creating ink precursors, which is the chemical solution used to pattern samples. And here's how they do that: by being inventive. They engineered their very own printing tool, creating a customized 2D printing station from the base on up.
Here, this is an optical microscope, allows us to view the sample during the patterning. We need it to be very stable, so we designed this little granite table, and it makes it stable and isolates vibrations from the floor. Then printing is much more precise because we need nanoscale precision. Representation of how printing is done on a silicon wafer. And a ray of cantilever writes lines on the surface of the silicon.
After patterning samples with a catalytic ink, they are loaded into the chemical vapor deposition system, where they are processed in what's referred to as a tube furnace.
So we slide it in here, slide it in a specific zone inside this furnace and inside this jumper. And then we slide the other source materials, which is served here as a precursor, in another zone, and should be in a specific position. We are going to upload or purging some gases.
Using different precursors, gases or solid, he says different materials crystalline at different temperatures. Next step, the atomic force microscope, to make sure they've been successful.
We have to analyze and see if we actually did create nanomaterials. Atomic force microscope allows us to create two-dimensional map of the surface. And this image is demonstration of ribbons that we patterned with the precursor ink. And after the synthesis, crystallization, they are now formed on the surface of the substrate.
They also needed to create an environment that will allow their innovations to work. Soundproofing foam lines the walls of this lab. The magnification of the measurements taken in this room is so great that even sound waves can distort the images. For instance, this atomic force microscope has 3 additional layers of isolation.
Nanomaterials are very difficult to handle. If you want to really test the strength of nanowire, you have to manipulate it. You have to hold it somehow with the miniaturized tweezers or manipulators and pull them apart to get fundamental properties of these nanowires. If we can build the building blocks of atoms or atomically thin structures, and we layer them, for example, or we sandwich them, or we manipulate them in some form, and we stack them, we create engineered materials. Materials that are not present in nature, you can't find them in nature. So this way we can actually tailor the properties of materials.
For Innovations, I'm Kathleen Berger.